Alright, so section 8.6 is about proportionality and proportional parts. So basically dividing things into parts that are proportional, which still deals closely with what we're dealing with as far as similar triangles go. So to get theorem 8.4, the triangle proportionality theorem says if a line that is parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. Alright, so if I've got one line like TU here that's parallel to QS, and it intersects the other two sides of the triangle, RQ and RS, then since it's parallel, it's going to divide these sides proportionally. So that if I take the length of RT over the length of TQ, that should be equal to the length of RU over US. So this part of this side over this part should equal this part of this side over this part. And then theorem 8.5 is just the converse to that, which says that if you have a line that divides two sides of a triangle proportionally, so you could have the lengths on these two sides. If you check to see if this side over this part of this side over this part is equal to this part of this side over this part, if those two fractions are equal to each other, then you know that TU is parallel to QS. And theorem 8.6, if we've got three parallel lines that intersect two transversals, then they're going to divide those transversals proportionally. So you have R, S, and T that are all parallel lines, and they're intersecting two transversals, L and M. And if that happens, then the parts that are divided in between those three parallel lines are going to be proportional. So this length from U to W over WY should be the same ratio as the length of VX over XZ. And the last one, theorem 8.7, says if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So I've got this ray here, and if it's bisecting angle C, then these two lengths of the side it divides, so AD and DB, or the length of AD over the length of DB, is going to be equal to the length of the other two sides over each other. And it'll, since we did AD, which is on the left side of the line, over DB, then we would do CA, which is on the left side of the line, over CB. So make sure that whichever side of the line you use to put on top for the first fraction, you use the other part that's on that side of the line on the other fraction as the top. Alright, so those are all the key theorems. Now we want to apply those. And some examples here. In the diagram, UI is parallel to VX. So these two lines, VX and UI, are parallel. Tells us that UV has a length of 3. UW, the whole side over here, is going to be 18. XW is 16, and we want to find the length of YX. We don't know what YX is, that's our X, so to speak. So, first off, we know that WU is 18 and VU is 3, so WV is going to be 18 minus 3, or 15, right? And so since those two lines are parallel, Vx and Uy, then that means that Wv over Vu, 15 over 3, is going to need to be equal to Wx over the xy length, which the xy length is what we're trying to solve for. So that's x. So we have a proportion, so just like all the other proportional stuff we do, we cross multiply, solve. So they give us 15x equals 3 times 16, or 48. And divide by 15. And our x is going to equal 3.2. Or that x actually is xy, right? So the length of xy is 3.2. The next one is basing it off of that converse given in the diagram. Determine whether PQ is parallel to TR. So in order for TR and PQ to be parallel lines here, we know that these parts over here and here should be proportional. So that means ST, which is 24, over TP, which is 9, should be equal to SR, which is 26, over RQ, which is 9.75. Alright, so in here, to solve this or determine if they're parallel, you got two options. You can try to reduce the fractions or plug it into a calculator and divide each one of those and see if you get the same answer, or we can cross multiply and see if the product of our cross multiplication is the same. And so that's my preference, is to cross multiply those. So we're going to have 24 times 9.75, which is 234, and 9 times 26, which is 234. So those are actually equal to each other. And so since those are equal, we can say that PQ is parallel to PR. So that cross multiplication product came out to be the same. Next one in the diagram, angle 1, angle 2, and angle 3 are congruent. So 1, 2, and 3, all three of those angles are the same. Which what that's telling us is that since all these angles are on the same transversal and they're all in corresponding locations, since they're congruent, that means that line AD, line BE, and line CF are all parallel to each other because their corresponding angles are all congruent. So since they're all parallel, that means we're using theorem 8.6, right? 3 parallel lines intersecting 2 transversals. So we know that this segment over this segment should equal this segment over this segment. So 6 over 9 should equal x over 8. So the length of AB over BC should equal DE over EF. We got our proportion. Once again, just solving the proportion. It's really what this chapter is all about mostly, is solving proportions. So you got 6 times 8, which is 48, is going to equal 9 times x. Divide both sides by 9. And 48 over 9 would reduce to 16/3 equals x, which is actually probably the more exact answer here. Or if you went ahead and divided it, 16 divided by 3 is going to give us 5.3333 repeating. So 16/3 is the more exact answer here, but both would work. And then the last example in the diagram, angle LKM is congruent to angle MKN. So this angle is congruent to that angle. And so since those two angles are congruent, that means that KM must be a bisector, right? It's bisecting angle LKN. And so since KM is a bisector, that means we are basing things off of theorem 8.7 here. So that these two sides that are divided by the bisector are going to be proportional with the other two sides. So that means, if we're trying to find the length of MN here, using the given side lengths to find the length of MN, then we know that 17 for KN over 3 for KL should equal MN over ML, right? So the length of KN over KL is going to equal MN over ML. Now the trick here is they gave us the total length for LN, and they didn't give us the lengths of any of the smaller individual parts. So if MN is what we're trying to solve for, we would call that X. And if MN is X and LN is 15, then to know what the length of LM is, or to have a value for LM, this is going to be whatever's left when you take X away from 15, right? Because if this was 9, we'd subtract that from 15 and we'd get 6 for this length, right? So LM is 15 minus the X. So now we can use those values and build the ratio just like we've got it here. KN over KL, MN over ML. So KN is 17. KL is 3. MN is going to be our X. And ML is 15 minus that X length. So once we've got the proportion, now it's just once again cross multiplying and solving for the X. So we have 17 times 15 minus X. It's going to equal 3X. Make sure we multiply that 17 times the whole quantity, 15 minus X. And 17 times 15 is going to be 255. 17 times X is 17X. 255 minus 17X equals 3X. Add 17X to both sides. I get 255 equals 20X. And divide by 20. And 255 divided by 20 12.75 equals our x, or the length of MN equals 12.75.